Okay, we saw in the last video that we could deal with exponential functions, and with u substitution it was often helpful to let u be the exponent, and that's not always the case. Let's look at these examples here. Let's try the integral of 1 plus e to the x all raised to the 4th power times e to the x with respect to x. And so when I first look at this, I say, well, could I possibly multiply things out? And I could. I could come in here and multiply this out 4 times. That's 4 binomials. Multiply all that out, then distribute the x across. Oh my goodness, that's a mess. So instead, I'm going to try to actually do a u substitution on this. Let's see if we can. Now, when we do a u substitution, remember I said in the last video that we have lots of choices. We saw that we could let u be the bigger piece or the piece that's being raised to a power. With trigonometric functions, we could let it be the angle, or we could let it be the entire trigonometric functions. We're going to see that with exponentials, we can let it be the exponent, or the bigger piece, or the piece that's being raised to a power. Lots of different choices here. The important thing is that whatever I pick for my u, that I see that I have my corresponding u prime. And in this case, it doesn't make sense to let it be the angle, because then I'm going to have 1 plus e to the u times, it's just a mess. It doesn't look like an e to the u times u prime. So why don't I let u be the bigger piece, or the piece that's being raised to a power, which in this case is just 1 plus e to the x. If that's the u, then the corresponding u prime that goes with that is just e to the x. Look at it. The derivative of 1 is 0, and the derivative of e to the x is e to the. So looking back at my original integral here, I see that this part is a u to the 4th, and this is a u prime. Again, you will always see me right underneath what it is I am integrating, because what I'm integrating is a u to the 4th, and when I integrate that, I'm going to get a 1/5 u to the 5th all plus c. So coming back in and putting in my u, this is going to give me a 1/5 times my u, which is 1 plus e to the x, all raised to the 5th power plus c. So here was a case where it didn't make any sense for us to let u be the angle in our u substitution. Let's try some more of those, because those are kind of interesting. Number 2. Let's try the integral of a negative 2e to the negative 2x divided by 1 plus e to the negative 2x with respect to x. And then let's go through the process. Well, this looks nothing like a basic rule, because I've got this big fraction there. And the only way we have to split up a fraction, or to get rid of a fraction, is either a long division or splitting the tops. We can never split the bottoms. So I can't do anything with that, and of course it doesn't look anything like a basic rule. I'm going to need to do a u substitution. Now, it's not going to make any sense to let u be the angle in this case, because if I do that, I'm going to wind up with a 1 plus u, e to the u and a u on the bottom and a u prime on top, and that does not look like my rule. My rule for e to the u says e to the u times u prime. That's not what I'm going to get no matter how I try to do that substitution if I let it be the angle. But how's about I go back to letting u be the bigger piece, or the piece that's being raised to the power. In this case, it's going to be the bigger piece, which is 1 plus e to the negative 2x. And if that's the u, then the u prime that goes with that is derivative of 1 is 0, and the derivative of e to the negative 2x is going to be a negative 2e to the negative 2x. Sorry about the color on that, because remember, when we differentiate an e to the u, we get the e to the u times the u prime. So let's look back at my integral and see what I have. Looks like I have the u here on the bottom, and I have the u prime on top, and when I integrate exactly u prime over u, that's going to give me the natural log of the absolute value of u plus c. So putting back in my u and my u on this, I'm going to get the natural log of the absolute value of 1 plus e to the negative 2x all plus c. And then the question becomes whether or not I can eliminate the absolute value, and the answer to this is yes, I can. Exponential functions by themselves are never negative. A negative exponent simply brings it to the bottom. That's e to the negative 2x is the same exact thing as 1 over e to the 2x. I have a little short video out there in your notes that reviews with you exponential functions. So if you don't remember that, go back and look at that video. But we do know that that is always positive. Adding 1 to it is always positive. So the final answer is going to be the natural log of 1 plus e to the negative 2x all plus c. Remember, it's perfectly okay to leave that e to the negative 2x since we don't know what x is, but you must, absolutely must, get rid of your absolute value on that. Okay, I want to do a comparison on this one, so let's see if I can fit all 3 of these across. I want to compare e raised to the sine of x times the cosine of x with respect to x to the integral of e to the x sine of e to the x plus 4 with respect to x, to finally the integral of e to the x cosine of e to the x plus 4 sine of e to the x plus 4. Oops, sorry about that, with respect to x. I tell you I'd run out of room on that. So let's look at these because they do look somewhat alike, but I can promise you that each and every one of these is going to be different. Looking across here, none of these are going to be a U substitution because, none of them are going to be a basic rule because none of our basic rules have exponentials and trigonometrics in it, which means all of them are going to be a U substitution. So let's see what we can do here. Let's start by looking at the first one. We have several choices for U. We can start by looking at letting U be the exponent. If I let U be the exponent, the U then is going to be the sine of x, which means the U prime that goes with that is going to be the cosine. That means that this first integral then is going to be an e to the u times u prime. And when we integrate that, we simply get e to the u plus c, or in this case, we're going to get e to the sine of x all plus c. And let me just circle here this so you can see that it's kind of outside of my problem. Okay, let's look at this second one here. And again, we're looking at a U substitution. It doesn't look like it's going to make a lot of sense to let U be the exponent on this. I do have an exponential and a trigonometric function in here. So let's see, why don't I try doing the angle? Let's let U be equal to e to the x plus 4. Then again, if that's the U prime that goes with that will be e to the x. Now looking at what that gives me, this part here looks like then the sine of u, and there's the u prime. And when we integrate the sine of u times u prime, we get minus the cosine of u, all plus c. So in this case, that gives me minus the cosine of e to the x plus 4, all plus c. So again, completely different choices for you there. And very helpful to write up top what it is I'm actually integrating. Don't let yourself decide ahead of time just because you see an exponential that it's necessarily going to be the exponent that's your u. It can be a variety of things. What you got to be mindful of is, do you have that u and do you have that u prime? And that's where you're going to make your decision. Let's go ahead and look at this last one here. I'm going to see if I can push this over a little bit because I did run myself out of room here. Now again, this is going to be a u substitution. So let's look at our choices for u. Well, it doesn't make a whole lot of sense this time to let u be the exponent once again. U being the angle is not going to make sense because I still can't integrate a sine and a cosine. But I can let u be the entire trigonometric function. And you do have an option on here. You can use either one. I'm going to let u be equal to the sine of e to the x plus 4. And if that's the u, then the u prime that goes with that is going to be e to the x cosine of e to the x plus 4. The reason for that is when we take the derivative of a sine of u, we get the cosine of that thing times the derivative of what's inside. So this stuff here will become the u prime. There is my u to the first, and what I'm integrating is u to the first times u prime. And so when I integrate that, I'm going to get a 1/2 u squared all plus c. So putting back in my u and putting it in the correct place, this is going to give me a 1/2 times the sine squared of e to the x plus 4 all plus c. So again, here's a good example of three separate integrals where they look very similar, but our choices for u vary widely depending on where our u prime sits. So don't try to get yourself boxed in. That's kind of the important thing on that one. One more type that I want to look at, and that is regular exponential functions. Let's look at the integral of 3 to the x with respect to x. And this is a basic exponential function, and we saw that when we integrate a to the x with respect to x, we get 1 over the natural log of a times a to the x plus c. So the a in this case is 3, which means we are going to get 1 over the natural log of 3 times 3 to the x all plus c. These functions are kind of difficult when they're new. We hadn't seen them in a while, but they are functions that we dealt with at some point. Again, go back and review the videos that I've got put out there for exponential functions.